Next chapter, probability. Now, will the player score the penalty? Yes? No? Of course, there is no way to tell that with certainty. There are chances he might score and chances that he might not. Probability is about chance. How likely or unlikely is it that an event will happen? Think about this. How likely is it that if today is Monday, tomorrow will be Thursday? Strange, isn't it? And if today is Monday, how likely is it that tomorrow will be Tuesday? Sensible, right? In these two questions, we have looked at the range of probability measure. The answer to the first question is impossible. If today is Monday, there is no way tomorrow can be Thursday. Something that is impossible has a probability value of 0. The answer to the second question is certain. If today is Monday, tomorrow will definitely be Tuesday. The probability value of this is 1. So probability can be anywhere between 0 and 1. And we can show this on a probability scale. Probability can be written as a decimal number, a fraction, or a percentage. But the key thing to remember is that probability can only have values from 0 to 1, including these values, or 0 to 100%. You should use these facts to check your answer when calculating probability. If your answer is less than 0 or larger than 1, then it is wrong. There are two types of probabilities, experimental and theoretical. Experimental probability is the probability of an event that can be determined from past experience. Back to our football, you might actually be able to predict the chances that the player will score. If he has scored 4 out of the last 5 penalties he has taken, you would say the chances of scoring this one are 4 out of 5. And so the probability is 4 over 5 or 0.8 or 80%. For example, a die is a cube whose faces are numbered 1 to 6. The die is cast and the number on the top face is recorded. If the die is cast 30 times and the results recorded in this table, find the probability of obtaining A, an even number, B, an odd number, and C, a prime number. In the solution, even numbers between 1 and 6 are 2, 4, and 6. The frequency of 2 is 5, the frequency of 4 is 8, and the frequency of 6 is 3. If you add them, you have 16. The total number of trials was 30. And so the probability of obtaining an even number is 16 over 30, which can be simplified to 8 over 15. B, odd numbers between 1 and 6 are 1, 3, and 5. The frequency of 1 is 4, 3 is 7, and 5 is 3. In total, there are 14 of them. So the probability of obtaining an odd number is 14 over 30, which can be simplified to 7 over 15. Lastly, prime numbers. Prime numbers between 1 and 6 are 2, 3, and 5. The frequency of 2 is 5, that of 3 was 7, and that of 5 was 3. In total, there were 15 of them. And so the probability of obtaining a prime number is 15 over 30, which simplifies to a half or 1 over 2. Theoretical probability is the probability of an event based only on expectations rather than experiments. I went to a shop and bought a packet of sweets. In the packet, there were 4 red sweets, 5 blue sweets, and 2 green sweets. Now I pick one sweet from the packet, only one. What is the probability of picking a green sweet? This is written in shorthand this way. Choosing green in this case is the event. What's the probability of this event? There are 2 green sweets. We have in total 2 plus 4 plus 5, giving us a total of 11. So the probability of choosing a green sweet is 2 over 11, or 0.1818, or 18.18%. And what's the probability of choosing a red sweet? In this case, red is the event. There are 4 red sweets and 11 sweets in total. So the probability of choosing a red is 4 over 11. In general, the probability of an event is the number of times the event occurs over the total number of possible outcomes. It is important to keenly read the questions on probability, because even with this understanding, simple common sense can evade you if you are not careful. Take a look at this. This bag contains 5 green balls, 3 blue balls, and 2 red balls. So in total, we have 10 balls. If you picked one ball, the probability of picking a green is 5 over 10. The probability of picking a red is 2 over 10. And the probability of picking a blue is 3 over 10. That's simple. Suppose now you are to pick 2 balls, one after another without replacing it. If you picked a green ball, the probability of that was 5 over 10. It is important to note that because the ball is not being returned before picking a second ball, the total number of balls have reduced to 9. So in the second picking, the probability of picking a red is 2 over 9, the probability of picking a blue is 3 over 9, and the probability of picking a green is 4 over 9. Suppose in the second picking you chose a red ball. Now in the bag there remains 8 balls, and so if you go for the third picking, the probability of picking a red is 1 over 8. The probability of picking a blue is 3 over 8, and the probability of picking a green is 4 over 8, and on and on. So take note of that. It is called successive picking without replacement. Next, the possibility space. Possibility space is the list of all possible outcomes of an event or events. Let's say I toss 2 coins. Each coin has a head and a tail. So in one coin, there are 2 possible outcomes, a head and a tail. And on the other coin, there are also 2 possible outcomes. When we multiply 2 by 2, the answer 4 is the number of possible outcomes. The possible outcomes from tossing the coins are head-head, head-tail, tail-head, tail-tail. We can use shorthand notation HH, HT, TH,
TT.
In another example, we have 2 spinners. One is 1, 2, and 3. The other is colors, blue, red, and green. On one spinner, there are 3 outcomes, 1, 2, and 3. On the other, there are 3 outcomes, blue, red, and green. When we multiply 3 by 3, The answer 9 is the number of possible outcomes. These are 1 blue, 2 blue, 3 blue, 1 red, 2 red, 3 red, 1 green, 2 green, 3 green. When listing the outcomes, you do it systematically. Notice we first listed blue outcomes, then red outcomes, and then green outcomes. It makes it easy for you to follow what you are doing and you don't miss any possible outcome. You can also list the possible outcomes on a sample space diagram, which is simply a table. In the first example, we can have a table like this one. And also for the second example. This table uses columns for colors and rows for numbers. It doesn't matter if you use them the other way round. Next, continuous probability. Sometimes the possibility space may be a length, area, or volume. Such possibility space is said to be continuous. For example, this diagram shows the journey traveled by a car. The car moves from town A to B such that it can stop anywhere along the path. Find the probability that the car stops between A and B. The probability that the car stops between A and B is the ratio of the distance AP to AB, and therefore, the probability that the car stops between A and B is equal to the length AP over the length AB. That is 50 kilometers over 130 kilometers, which gives us 5/13. Another example. This diagram shows a square whose size is 2 centimeters inside a rectangle of 6 centimeters by 7 centimeters. What is the probability that a point selected at random from the rectangle lies within the square? In our solution, the selected area can lie anywhere within the rectangle. The area of the rectangle is 42 centimeters squared, that is 6 times 7. 42 centimeters squared, the area of the rectangle forms the possibility space. The probability that the point selected lies in the square depends on the area of the square, which is 2 by 2, that is 4 centimeters squared. So the probability that the point lies within the square is equal to the area of the square over the area of the rectangle, that is 4/42, which gives us 2/21. The probability of an event is a ratio and has no units. Next, mutually exclusive events and the addition rule. In probability, the outcome of a process is called an event. Mutually exclusive events are events that cannot happen at the same time. When going to school, you are either late or on time. If you play a game, you either win or lose. When you flip a coin once, you either get a head or a tail. You cannot get a head and a tail at the same time. These are examples of mutually exclusive events. Mutually exclusive events could be more than 2. Let's go back to our bag with balls. We are picking a ball at random. Because we are picking only one ball, we cannot pick a red, green and blue at the same time. So the 3 events, picking a red, picking a green and picking a blue, are mutually exclusive. If one occurs, it means the others did not occur. In this bag, the probability of picking a red is 2/10. The probability of picking a blue is 3/10. And the probability of picking a green is 5/10. If we add these probabilities together, we get 2/10 plus 3/10 plus 5/10, which is equal to 10 over 10, which is the same as 1. For mutually exclusive events, the total probabilities must add up to 1. And so if the probability of being late for school is 0.24, the probability of not being late is 0.76. That is 1 minus 0.24, because late and not late are mutually exclusive events, and therefore their probabilities must add up to 1. Let's stick with the bag for a moment. Suppose you wanted a red ball. The probability is 2 over 10, quite a low chance. What if you wanted a blue or a red? Now that increases your chances of getting it, because either blue or red is okay with you. Notice the use of the word or, because only one can happen at a time. It's different from saying blue and red. If A and B are mutually exclusive events, then the probability of A or B happening is equal to the probability of A happening plus the probability of B happening. And so in our example, the probability of picking a blue or a red is equal to the probability of picking a blue plus the probability of picking a red. That is equal to 3 over 10 plus 2 over 10, giving us 5 over 10. Let's take an example. A basket has 6 mangoes, 4 oranges, and 5 lemons. A fruit is picked at random. Find the probability that it is a citrus. Now, oranges and lemons are citrus fruits, and so in this example, we find the probability of picking an orange or a lemon. The probability of picking an orange is 4 over 15. There are 15 fruits in total and we have 4 oranges. The probability of picking a lemon is 5 over 15. And so the probability of picking an orange or a lemon is the sum of the individual probabilities. That is 4 over 5 plus 5 over 15, and that gives us 9 over 15, which is equal to 3 over 5. Another example, a number is chosen randomly from 1 to 9. Find the probability that A, it's an even number, and B, it's a prime number. In our solution, there are 10 numbers in total. The probability of picking any number is 1 over 10, therefore. In A, even numbers are 2, 4, 6, and 8. So we calculate the probability of picking a 2, or picking a 4, or picking a 6, or picking an 8. That is equal to the probability of picking a 2 plus the probability of picking a 4 plus the probability of picking a 6 plus the probability of picking an 8. That is 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10, and that gives us 4 over 10. B, prime numbers from 1 to 9 are 2, 3, 5, and 7. So we calculate the probability of picking a 2, or a 3, or a 5, or a 7. That is equal to the probability of picking a 2 plus the probability of picking a 3 plus the probability of picking a 5 plus the probability of picking a 7. That is 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10, which gives us 4 over 10. Next, independent events and the multiplication law. Now, 2 events are independent if the occurrence of one event does not affect the occurrence of the other. For example, in our case, when going to school, being late and not being late are mutually exclusive events. They cannot happen at the same time. But now, if you are late for school, you might be punished or you may not be punished. Being late and being punished are two independent events. One does not affect the other. You may be late and be punished, but you may also be late and not be punished. Two independent events can occur at the same time, and we use the word and, like late and punished or late and not punished. If A and B are independent events, then the probability of A and B is equal to probability of A times the probability of B. For instance, if the probability of being late is equal to 1 over 4 and the probability of being punished when late is 5 over 7, then we can calculate the probability of these independent events. So the probability of being late and being punished is equal to the probability of being late times the probability of being punished. That is 1 over 4 times 5 over 7. And that gives us 5 over 28. Also, we can calculate the probability of being late and not being punished. Note that punished and not punished are mutually exclusive. And so if the probability of being punished is 5 over 7, then the probability of not being punished is 2 over 7. And so the probability of being late and not being punished will be equal to 1 over 4 times 2 over 7, which will give us 2 over 28. Back to the balls in the bag again. If we are only picking one ball, then picking a red, a green, and a blue are mutually exclusive events. They cannot occur at the same time. But if we are picking more than one ball in succession, then the second picking is independent of the first picking. Suppose you picked a green ball in the first picking. That does not in any way affect the second picking. You can still pick any other ball from the basket, like a red or even another green. If you had one coin, the occurrence of a head and a tail are mutually exclusive. They cannot occur at the same time. But if you had two coins and you toss them, the occurrence in one coin is independent of the other. It means if the first coin gives a head, the other doesn't have to give a tail. They are independent. And so the probability of getting a head and a tail is equal to a half times a half, which gives us 1 over 4. Probability questions often combine both independent and mutually exclusive events. For example, if two coins are tossed, find the probability that the two coins give similar results. That means we find the probability that both coins will give heads or tails. So we have probability of head and head, or the probability of tail and tail. That is the probability of a head times the probability of a head plus the probability of a tail times the probability of a tail. A half times a half plus a half times a half gives us 1 over 4 plus 1 over 4, and that gives us 1 over 2. If the coins were tossed in succession, what is the probability that they produce different results? This means that we look for the probability of either tail and head or head and tail. And therefore we have probability of tail and head or probability of head and tail. That gives us probability of tail times the probability of head plus probability of head times the probability of tail. That is a half times a half plus a half times a half, giving us a half. For this basket with balls, if two balls are picked in succession without replacement, find the probability that both have the same color. In this case, we are looking for the probability of blue and blue, or green and green, or red and red. Remember, in successive picking without replacement, the number of balls or items reduce with each picking. And so we shall have the probability of blue and blue. First picking, blue is 3/10. Second picking, if you had picked up blue, then the number of blues has reduced to 2, and the total number of balls have also reduced to 9. So times 2/9. Or the probability of green and green. Green in the first picking, the probability is 5/10. If you have picked a green in the first picking, then the total number of green balls have reduced to 4, and also the total number of balls have reduced to 9, so times 4/9. Plus the probability of picking a red and a red. In the first picking, there are 2 red balls, and so the probability is 2/10. If you have picked a red ball in the first picking, then in the second picking, the number of red balls have reduced to 1, and also the total number of balls is 9, so times 1/9. Finally, the tree diagrams. Now, a useful way of sorting out problems of probability that involve more than one event is to draw a probability tree diagram. Consider a fair coin tossed twice. The outcomes can be represented on a tree diagram as shown on your screen. In the first toss, the probability of obtaining a head is a half, and that of obtaining a tail is also a half. In one throw, the events are mutually exclusive. Only one can happen at a time. And then we go to the second throw. Again, the probability of obtaining a head is a half, and that of tail is also a half. The events in the first throw and those in the second throw are independent. The outcomes are written at the end of the branch, and their probabilities are written along the branch. The sum of the probabilities at any branch from the same point is 1 because they are mutually exclusive, no matter how many outcomes there are for one trial. This is the most important feature of the probability tree diagram. Let's take an example. A box contains 4 white balls and 5 blue balls. 2 balls are drawn at random, one after another with replacement. Illustrate this information on a tree diagram and find the probability that A. Both balls are white, B. Both balls are of the same color, and C. Both balls are of different colors. Now this is a tree diagram. In the first picking, the probability of picking a white is 4/9, and the probability of picking a blue is 5/9. And the same for the second picking. So this is a representation of the information on the tree diagram. A. There is only one path with both balls being white. Therefore, the probability of white 1, white 2 is equal to 4/9 times 4/9, giving us 16/81. B. There are 2 paths with the same color, white white or blue blue. Therefore, we shall have P white white or P blue blue. That is equal to 4/9 times 4/9 plus 5/9 times 5/9. That gives us 16/81 plus 25/81. And that is equal to 41/81. And C, there are also 2 paths with different colors, either white blue or blue white. Therefore, we calculate the probability of white blue or blue white. That is equal to 4/9 times 5/9 plus 5/9 times 4/9. That gives us 20/81 plus 20/81, giving us 40/81.
The way we teach it in university and in high school as well, and colleges, is if you fall behind, you're in desperate trouble. That if you miss a class or miss an idea or don't do your homework, you go to the next class and the teacher assumes you know it, but it's like Greek to you. And so the biggest challenge is not falling behind, and the strategy is do whatever needs to be done so you don't fall behind. Seek help wherever you can find it, from students, from student help centers, from the teacher, from the teaching assistant, wherever you can get it. Because if you fall behind, it's like you're missing a floor in the building, you're missing a brick in the wall, and you just can't build the second floor without a good understanding of the first floor. It applies course to course, it applies class to class. Miss a class, one class, maybe that's fine. Miss 2 or 3 for whatever reason, the rest of they're speaking a foreign language for you, and you just have to make it up, or going to class has no point. If you don't go to class, it just gets worse. It snowballs, and once it starts going downhill, you're in trouble.